So first of all, very good evening to everyone, and today I will going to discuss week 4. In the last week I have covered week 3, in which 3 lectures are there, lecture number 7, 8 and 9, and in today's session I will discuss 2 lectures, which is lecture number 10 and lecture number 11. So in week 4, there are 2 lectures, that is lecture number 10, which is on Mohr circle, and lecture number 11, which is on concept of strains. Okay, so first of all I will briefly explain the concepts that is already covered in the lecture. I have not done any derivation. I will not do any derivation in this session. I will only brief the concepts that is already covered in those lectures. So if you have any doubt regarding the derivation and all the detailed explanation, you can refer to the lectures. So yeah, let's start. So first of all, in the last week also I have covered examples based on the Mohr circle, but some of the concept was still remain. So the remaining concepts that is covered under the Mohr circle will be discussed here. So yeah, so in the last session we see that the Mohr circle, in the Mohr circle we can find out the maximum principal stress and the planes and the maximum shear stress through the Mohr circle, and the formula for that is given by, so normal principal stress, maximum principal stress is given by sigma is equal to sigma xx plus sigma yy upon 2 plus r cos 2 phi minus 2 alpha, where r is the radius of Mohr circle. Similarly, maximum shear stress is given by r sine 2 phi minus 2 alpha, where radius is given by root over sigma xx minus sigma yy whole square, sigma xx minus sigma yy by 2 whole square plus tau xy whole square, and the phi, that is angle tan 2 phi, is given by 2 tau xy upon sigma xx minus sigma yy. Maximum principal stress and maximum shear stress formula. So this has already been discussed in the last session. So I just write here the formula that is being used in the following problem that I will discuss. Next is Mohr stress plane. In this lecture, Mohr stress plane will be discussed. So we can find out the planes on which the normal stress acting or the maximum shear stress will act. So this, suppose we have this x-axis and y-axis. As we know that along the x-axis shear normal stress is plotted, and in the along the y-axis shear stress is being plotted. Okay, and suppose if we know the three principal stresses, that is lambda 1, lambda 2 and lambda 3. So these are the three principal stresses where shear stresses are 0. And if we know the center of these two more circle, so we can draw a circle using that two corner points. Similarly here we can draw another circle using these two corner points. Okay. And there is another circle from the endpoints lambda1 and lambda2. We can draw another one circle, that is lambda1 and lambda2. So yeah. Okay. So this is the three circle that is being drawn using three principal stresses lambda1, lambda2 and lambda3. And on each plane there is one maximum shear stress. There is one maximum shear stress, that is the radius of the circle. So if we found the maximum shear stress on this plane, that is formed from the lambda1 and lambda2 principal stress, we can find out the maximum shear stress using this formula lambda1 minus lambda2 upon 2. Similarly, if we find out the maximum shear stress on this plane, which is formed using lambda2 and lambda3, so in this case we can find out the radius of the maximum shear stress, which is nothing but the radius of the Mohr circle, which is given by lambda2 minus lambda3 upon 2. And the remaining portion that is covered under plane number 3. And if you want to find out the maximum shear stress on this plane, so it is given by lambda1 minus lambda3 upon 2. Okay. So these three planes correspond to three principal stresses. On each plane, there is a one principal stress and one shear stress, maximum shear stress. Okay. So here we can write sigma or tau, that is normal and shear stress for arbitrary planes occupy the shaded region. That means if we want to find out the shear stress in any other plane than the plane corresponding to maximum stresses, we can find out using that shaded region. That is, the shaded region corresponds to any arbitrary plane. If we ask a question that we want to find out the plane, any arbitrary plane which is not aligned along the principal direction, so using that plane, that is a shaded region plane, we can find out the normal stresses acting on that particular plane. So from this graph, we can comment on which the principal stress component are point of maxima and which of them are point of minima. So here you can see lambda1 is the global maxima. That is, you can see that lambda1 is the global maxima for all the three planes, and lambda3 is the global minima. Otherwise, if we consider only this plane, so here lambda2 is the global maxima and lambda3 is the global minima. But if we consider all the three principal plane, then we get lambda1 is the global maximum principal stress, and the minimum principal stress is given by lambda3. And the maximum principal stress, that is lambda1, means that the component of traction, that is sigma on this plane, is highest among all the other planes. So that is why lambda1 corresponds to the global maxima for this all the plane. Now based on this Mohr circle, I will explain some special cases. So the first special case is special case 1. So the first special case when two of the principal stress are equal. That is, suppose lambda1 is greater than lambda2 and lambda2 is equal to lambda3. That is, here two of the principal stresses are equal. So in this case, what happens to the Mohr circle? So I just draw the Mohr circle corresponds to this state. So here we know that lambda2 and lambda3 are equal, so we can point out anywhere here, and lambda1 is, so here it is mentioned that lambda1 is greater than lambda2 and lambda3. So lambda1 is suppose lying here, and lambda2 and lambda3 suppose are here. Okay, so here you can see there is only one circle that we can draw, that is only this circle. So the three circle reduces to a single circle when lambda2 equal to lambda3. That means we have just one circle corresponding to lambda2, lambda1 and lambda2, and the stress plane just reduces to a circle. So this is one of the special case. And suppose what happens to the here also you can see that there is a shaded region. So in this case, what we can say about the shaded region? So suppose there is a some lambda2 value which is not equal to lambda3. Okay, so it has some lambda2 value, so it have some shaded region. But if we then the lambda2 value equal to lambda3, then the shaded region also vanishes. That means there is only a single circle which exists when lambda2 equal to, that means when any of the two principal stresses are equal, then only single circle, Mohr circle will exist and the shaded region will vanish. The next case is when all the three principal stresses are equal. That means lambda1 equal to lambda2 equal to lambda3. So in this case, if we plot in the Mohr circle, so we know the lambda1, lambda2 are the principal stresses value, so it can be plotted in the x-axis. So lambda1 equal to lambda2 equal to lambda3. So you can see that there is no circle draw from this point, and the single circle also reduces to the point. That means the circle when lambda2 and lambda3 value approaches lambda1, that is when it becomes equal to lambda1, then the circle also vanishes to a single point. So this case happens when there is a many example when all the three principal stresses are equal. So one of the example that is already discussed in the lecture is the hydrostatic pressure which is acting at any point inside the fluid. Okay, so in that case, when we see the principal stress at a point on any particular plane in a fluid, we can see that the principal stresses are equal, which is equal to the hydrostatic pressure of the fluid. Okay, so this is about the Mohr circle, special cases of Mohr circle. Next, that is covered under lecture number 10 is the stress invariants. So as we already know that stress invariants, so coming to the stress invariants, first we know that as I mentioned earlier also that the stress tensor, which is something independent of the coordinate system, but if we write the component of stress matrix, it is somehow dependent in the coordinate system. So but there are certain thing that is also independent of the coordinate system. That means the component, that means some special component may also be independent of the coordinate system. But as you know that stress matrix is dependent on the coordinate system. So that means if we change the basis of the coordinate system, the stress value, that is a component of stress value, will also change. So what is stress invariance? So stress invariants are those invariants which is independent of the coordinate system. These are the some components value of the stress matrix which is independent of the coordinate system. That means if we change the coordinate system, then if we take the invariants in different coordinate system of the same stress tensor, we found that their values are same. So that is called the stress invariance. So stress invariance has three parts. That means it has three invariants: first invariant, second invariant, and third invariants. So I will just write the stress invariants. That is the three stress invariants. So we have three stress invariants. The first stress invariance is nothing but summation of all the principal stresses, lambda 1 plus lambda 2 plus lambda 3. We can also say that, so the first invariant is summation of all the principal stresses. The second invariant is lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. That means the product of two stress invariant, that is the product of two stress invariant, lambda 1 lambda 2, summation of the product of two stress invariants, principal stresses, lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 3 lambda 1. And the third stress invariant is the product of all the stress invariant, product of all the three principal stresses, that is lambda 1 lambda 2 and lambda 3. It is also equal to, it can also be same as determinant of stress tensor. Okay, it can also be same as trace of stress tensor. Okay, if we want to find out the first stress invariant, we simply take the trace of the sigma matrix which is formed by the stress tensor. We can get the first invariant. Second invariant can also be written as in this way, in terms of component of stress matrix, that is given by sigma 2 2 sigma 3 3 plus sigma 1 1 sigma 3 3 plus sigma 1 1 sigma 2 2 minus sigma 1 2 square minus sigma 1 3 square minus sigma 2 3 square. So in terms of the stress component of a stress matrix, it can be written in this way. Okay, so these are all the three stress invariants of a stress tensor. The next thing, definition is the octahedral stress component. Octahedral stress components. So what is octahedral stress component? So basically octahedral plane, first we define the octahedral plane. So octahedral plane are the faces of octahedron having 8 faces whose normal have the following form. So octahedral stress component corresponds to octahedral plane, which is nothing but the faces of octahedron, which has 8 faces. So octahedral planes are the faces of octahedron having 8 faces, whose normal is given by following form. So the normal of octahedral planes is given by plus minus 1 by root 3 plus minus 1 by root 3 plus minus 1 by root 3. So it has 8 octahedral plane, and each octahedral plane corresponds to one normal. So it can be found in this way, and the normal is given by this equation, normal of octahedral plane. And the component of normal and shear component of traction in octahedral faces are called the octahedral stress components. So octahedral plane has also normal and shear component, and each stresses are called the octahedral stress component. So first, the normal component of octahedral plane is given by, so octahedral normal component of octahedral stress component. Normal component of octahedral planes, component of traction on octahedral planes. So the derivation is already discussed in the lecture, so I just write the formula here. So normal component of traction on octahedral plane is equal to lambda 1 plus lambda 2 plus lambda 3 upon 3. So this is the normal component of traction on octahedral plane. Which can also be written as, which is same as first invariant of stress tensor upon 3, because lambda 1 plus lambda 2 and lambda 3 plus lambda 3 is the first invariant of stress tensor. One thing I would like to mention here, that octahedral plane are always defined related to the principal coordinate system and not related to any general coordinate system, that is E1, E2 and E3 coordinate system. So I write one point here, important note, that octahedral planes are always defined relative to the principal coordinate system and not relative to any general coordinate system. So the shear component of traction on octahedral plane is given by shear component of traction on octahedral plane. So shear component of traction on octahedral plane is given by root over root 2 by 3 root 2 by 3 root over first invariant of a stress tensor whole square minus 3 times second invariant. So this is the octahedral shear component of traction on octahedral plane. So using these two formula, we can find out the normal and shear component of traction on octahedral plane. Okay. The next thing that will be discussed is the hydrostatic and deviatoric part of stress tensor. Hydrostatic and deviatoric parts in stress tensor. So the hydrostatic part is given by this formula, 1 by 3 first invariant of stress tensor times identity. and that is the hydrostatic part plus, and the deviatoric part is given by stress tensor minus 1 by 3 first invariant of stress tensor times identity. Okay, so this is the hydrostatic part and this is the deviatoric part. And here we can derive that the first invariant of the deviatoric part is 0. So I can also write here first invariant of deviatoric part is 0. As you can see here, that hydrostatic part is multiplied with identity tensor. So it means that it has only normal component of traction, whereas the deviatoric part contains the shear part. So basically, the decomposition of a stress tensor in a hydrostatic and deviatoric part means that the first part denotes the normal component of stress matrix, and the second part contains the information about the shear component of stress matrix. Okay, so this contains the information about normal stress, that is normal traction, and this is the state of pure shear. So state of pure shear, deviatoric part is also known as state of pure shear, and the hydrostatic part also known as the normal, or we say the normal traction, only normal traction state, means state of normal stress. So this is all about lecture number 10. So these all topic already covered in lecture number 10, and the next lecture that is covered under week 4 is lecture number 11, which is on more concept of strengths. So as we know that any body when deformed from its reference state to deformed state, there is a change in stress at every point in the body. Along with that, strain also varies in the body. So basically in this lecture, concept of strain has been discussed. So for the detailed derivation, you can go through the lecture, and I only cover here some important concept of the lectures. So the first concept that is discussed here is about the deformation gradient tensor. So it is given by F. So it is denoted by F, big F, and it is a second order tensor. So therefore I write below 2 tilde, and it is given by gradient of F, where F is any general vector quantity. And when we decompose it, when we break it in different in tensorial form, it can be written in this way: del F upon del x1 tensor product E1 plus del F upon del x2 tensor product E2 plus del F upon del x3 tensor product E3. And in initial notation it can be written as summation over I summation over j del f I upon del x j ei tensor product ej. So this is the deformation gradient tensor. So it basically does, it maps the undeformed line element into deformed line element. So suppose we have a body in which there is a point x in the reference state, and after deformation it moves to some other location, that is x. And if we want to know the map, how it is deformed, from how it is deformed, this point, how it moves from this position to the current position, that is the deformed position. I have denoted the deformed position by small x and the undeformed position of that material point by big X. So it basically maps the two state, the deformed and the undeformed state. So f is given by grade of. So here we can define one function which is f, which is also called deformation map, and it maps the undeformed coordinate into the deformed one. So here f is the called the deformation map. And if we take the gradient of f with respect to undeformed coordinates, we can find out the deformation gradient tensor. Deformation gradient tensor also be written as in terms of displacement component. So deformation gradient tensor can also be written as f equal to identity tensor plus gradient of u. So what is u? U is the displacement vector, and x is the position vector in the deformed state. Okay, and big X is the position vector in undeformed state. So it can also be written in this way, deformation gradient tensor. So this two topic has been discussed in lecture number 11. The first one is the deformation gradient in terms of deformation map, and the second is the deformation gradient tensor in terms of displacement vector. So these two formula will be used in solving the problem related to the deformation gradient, and find out the strain at each point in the body. So the concept of strain will be furthermore discussed in the coming lectures. So this is only about the lecture number 11. So these two lectures, based on these two lectures, lecture number 10 and lecture number 11, I will solve some problem through which you can better understood the concept, and basically this concepts, this problem, through this problem you can get to know better that uh, how this what the meaning of these definitions, and how you solve any type of problem related to uh, Morse circle and deformation gradient tensor. Okay, so let's begin the problem session, that is problem number. So first of all I will solve the first problem, that is problem number 1. So this problem is based on the Morse circle concept. So the problem is, Suppose the state of stress at a point is as follow in x, y, and z coordinate system. Okay, so the state of stress at a point is as follow in x, y, and z coordinate system. So the question is, the first question is, find out the center and radius of corresponding Mohr circle. The next question based on the above statement is, find out normal and shear stress on a plane whose normal makes an angle 15° anti-clockwise from the x-axis. Sorry, I missed out the stress tensor, that is the stress matrix. I forgot to write here, so I just write the stress matrix, that is sigma is equal to -2 4 root 3 0 4 root 3 6 0 0 0 and 4. So this is the stress matrix, and based on this stress matrix we have to find out the center and the radius of the Mohr circle, then find out the normal and the shear stress on a plane whose normal makes an angle 15° anti-clockwise from the x-axis. The next question is question number C. What are the values of the principal stress components? So we have three questions based on the above statement. So what the problem is, suppose the state of stress at a point is as follow in x, y, and z coordinate system. So the state of stress at a point is given here in x, y, and z coordinate system. So the first question is, find out the center and radius of the corresponding Mohr circle. The next question is, find out the normal and shear stress on a plane whose normal makes an angle 15° anti-clockwise from the x-axis. And the third question is, what are the value of the principal stress components? Okay, now so first of all we have to draw the Mohr circle based on the stress matrix that is given in the problem. So let's draw the Mohr circle first. So this is the shear stress and this is the normal stress. Now the question is, find out the center and radius of the corresponding Mohr circle. So as we know that radius of the Mohr circle, center of the Mohr circle is given by center of Mohr circle is given by sigma 11 plus sigma 22 upon 2 comma 0, which is same as, what is sigma 11 is, sigma 11 here is -2 and sigma 22 is 6. So therefore it becomes -2 plus 6 upon 2 comma 0, that is nothing but 2 comma 0. So we find out the center of the Mohr circle, that is at 2 comma 0. The next question is radius of the Mohr circle. So we know the center of the Mohr circle. Now we also know the corresponding point, the corresponding value of normal and shear stress on the even plane, that is -2 comma 4 root 3. So first we plot this point, that is -2, that is on the even plane. We know the value of the shear stress and the normal stress, that is -2 comma 4 comma 3, 4 root 3. So first we plot that point -2 comma 4 root 3. It lies something here, somewhere here, -2 comma 4 root 3. And we know that if we join this point with this point, we will get the radius of the Mohr circle. So I just join these 2 points. Yeah, so this, we will get the radius of the Mohr circle, and with this center and with this radius we can draw the circle. So basically with keeping this as a this point as a center and this is as a radius, we can draw a circle here. So this is the complete Mohr circle. Now to find out the radius, we basically use the distance formula, because we know these 2 points and we have to find out the distance between these 2 points, which is basically the radius of the Mohr circle. So the radius of Mohr circle, this is the first problem. So radius of Mohr circle R is given by, we basically use the distance formula, that is 2 minus 5 minus 2 whole square plus 4 root 3 minus 0 whole square, that is 2 minus of minus 2 whole square plus 4 root 3 minus 0 whole square. So after calculating this, we will get the value equal to 8. So the radius of the Mohr circle is of 8 unit. So this is the radius which is of 8 unit, and this is also the radius which is of 8 unit. So from this to this there is a distance of 2 unit, and this is of 8 unit. So what is that point, which is basically 8 plus 2, that is 10 comma 0. Now coming to this point, this is the distance of 2 unit and this is the distance of 10 unit, because it is the radius of the circle. So 10, and this is the center of the Mohr circle. So this is 2 and this is, what is the distance of that circle? So this from here to here, the total distance is of 10 unit. But in the opposite direction. So this is 10, sorry, radius is of 8 unit. So yeah, this from here to here it is of 8 unit. From this point to this point, the total distance is 8 unit, and from this point to this point, the distance is 2 unit. So what is that distance from this to this is 8 minus 2 plus 8, that is minus 6 unit. So it is minus 6 comma 0. Now coming to the next question that we have is find out. The next question is find out. So the first question we already get the result for the first question, the center and the radius of corresponding Mohr circle. We found out the center also and the radius of the corresponding Mohr circle also. And the second question is find out the sigma and tau on a plane whose normal makes an angle 15 degree anti-clockwise from the x-axis. So the question says that we have to find sigma and tau on a plane whose normal makes an angle 15 degree anti-clockwise from the x-axis. So 15 degree anti-clockwise from x-axis physically means that 30 degree clockwise from the x-axis. So this is your x-axis. Basically this is the x-axis, or we say even plane. This is the x-plane basically. And in this, the question says that we have to find sigma and tau on a plane whose normal makes an angle 15 degree anti-clockwise from the x-axis. So in the Mohr circle, it means that 30 degree clockwise from the x-axis. So we take 30 degree clockwise. Now if we take 30 degree from the clockwise, as we know already that what is the angle, this one. So this is 8, radius is of 8 unit, and this is of, this distance is of 4 root 3 unit. So what is the angle theta here? So theta is basically sine theta is p by h, that is 4 root 3 by 8, that is root 3 by 2. So theta becomes 60 degree. So this is 60 degree, and then we have to move a 30 degree angle as according to the question. So this completely make an angle of 90 degree. Okay. So on this plane, so the question says that on this plane we have to find out the sigma and tau value. Okay. So as you can see here, this is the plane of maximum shear because there is no normal stress at this point. As you can see from this line, it's a straight line. So there is no normal stress, there is only shear stress exist, maximum shear stress exist. So from this figure we can see that there is a maximum shear stress point of 8 unit, which is equal to the radius of the circle, and this is the normal stress, and this is the value of shear stress. So on this plane, the value of sigma and tau is given by question number B. So first I will write here in Mohr circle, (15° anti-clockwise from x-axis physically means 30-degree clockwise from x-axis. So I also move clockwise from the x-axis plane. So as we move 30-degree clockwise from x-axis plane, we can find out this straight line that I show here, and in this plane we have to find sigma and tau. So what is the value of sigma here? That is of 2 unit, and what is the value of tau here? That is of 8 unit. So sigma is equal to 2 units. Normal stress is of 2 unit, and shear stress on this plane is 8 units. So this is the answer. Now coming to the third part of this question, what are the values of the principal stress component? So this question asks that what is the value of the principal stress component? So as we know, the principal stress are nothing but the corner point of the Mohr circle on the sigma axis. So here we can see we have two corner points sigma on the sigma axis. The first one is here and the second one is here. And from the stress matrix we see that the third axis, the third principal plane is along the third coordinate axis, that is along the E3 axis. So the third principal stress is of 4 unit. We have to find only the other two stress component, principal stress component. The other two can be found using this Mohr circle, and it is given by the two corner points on the sigma axis. So the first value of principal plane is, so question number C. So principal stresses are, first one is sigma 1, or we say lambda 1 is equal to, so lambda 1 is basically the maximum principal stress, that is of 10 unit. Lambda 1 is 10. What is the value of lambda 2? Lambda 2 is -6. And what is the value of lambda 3? As the third principal plane lie along the third coordinate axis, so it is given by 4 units. So as given. So this is all about question number 1. So I hope everyone have understood this question. Now move on to the next question, that is for problem number 2. So problem 2 is also based on the Mohr circle. So the question is, the stress tensor at a point is denoted by the following matrix in Cartesian coordinate system. So the stress tensor is, the component of stress tensor is given by -7, 6 root 3, 0, 6 root 3, 5, 0, 0, 0, 3. So this is the component of stress tensor sigma that is given here. So based on this statement, we have 4 questions that we have to find. The first part of the question is, draw Mohr circle corresponding to this state for tractions in xy plane. Also, what are the principal stress component? What are the principal stress components and the direction of principal planes? And the direction of principal planes. Also, what is the maximum shear traction? What is the maximum shear traction? What is the maximum shear traction and on what plane does it act? And on what plane does it act? So this is the first question I am repeating here. Draw the Mohr circle corresponding to this state for tractions in xy plane. Also, what are the principal stress components and the direction of principal planes? Another thing that is have to find we have to find is what is the maximum shear traction and on what plane does it act? So this is the first part of this question. The second part is using Mohr circle. Using Mohr circle, find out the normal. Find out the normal and shear tractions on a plane whose normal lies in xy plane whose normal lies in xy plane and makes an angle of 15 degree from x-axis and makes an angle of 15 degree from x-axis in clockwise direction. So this is the second part of the question. I am repeating once again. Using Mohr circle, find out the normal and shear tractions on a plane whose normal lies in xy plane and makes an angle of 15 degree from x-axis in clockwise direction. The third part of the question is find out the octahedral normal and shear stress components corresponding to this state of stress corresponding to this state of stress corresponding to this state of stress. And the last part of this question is decompose Decompose the given stress. Decompose the given stress matrix into hydrostatic and deviatoric part. So this question has three parts, and it has given a stress tensor here, the component of stress tensor. The first part is to draw a Mohr circle corresponding to the state for traction in xy plane. Also the principal stress component and the direction of the principal plane we have to find out. In this question, we also have to find what is the maximum shear traction and on what plane does it act. The second part is using Mohr circle, find out the normal and the shear traction on a plane whose normal lies in xy plane and makes an angle of 15 degree from x-axis in clockwise direction. And the third question is find out the octahedral normal and shear stress component corresponding to this state of stress. And the last part of this question is decompose the given stress matrix into hydrostatic and deviatoric part. So let's begin with the solution. So first question is to draw the Mohr circle. So in this question we have to draw the Mohr circle. So this is the shear stress tau and this is sigma normal stress. So first begin with the center of the Mohr circle. So the center is given by center is sigma 11 plus sigma 22 upon 2 comma 0, which is sigma 11 is minus 7, sigma 22 is 5. So minus 7 plus 5, that is minus 2 upon 2, that is minus 1, minus 1 comma 0. So this is the center. So I will draw the center here, that is on at minus 1 comma 0. Now from the stress matrix we know the component of normal and shear stress on the even plane, that is on the x plane. So the component of normal stress on the x plane is minus 7 and the shear stress is component of shear stress is 6 root 3. So we plot this point on the Mohr circle minus 7 comma 6 root 3. So it lies somewhere here minus 7 comma 6 root 3. Minus 7 comma 6 root 3. And these 2 points, if we join these 2 points, we will get the radius of the Mohr circle. So basically I am joining these points. So this is the radius of the Mohr circle as per the question. Now using this radius and this center, using this radius and this center, we can draw the whole circle. So the circle, that is the Mohr circle, yeah. So this is the Mohr circle as per the question. So the first question is draw Mohr circle. We already draw the Mohr circle. To this state for traction in xy plane. Also, what are the principal stress component and the direction of principal planes? Okay. So first of all, we have to find out the radius of the Mohr circle. So radius of the Mohr circle is nothing but we can find out using the distance formula. So radius of Mohr circle. I am making it some smaller size so that it will visible in the complete screen. So yeah, this is the radius of the Mohr circle. So radius of minus 7,653 is here. This is the radius. So radius of Mohr circle R is given by minus 7 minus 1 whole square, that is 8 whole square, plus 6 root 3 minus 0 whole square, that is 6 root 3 whole square. So if we calculate this, we will get 12. So the radius is of 12 units. So the first part of the question, in the first part, we also have to find the principal stress along with the direction of principal planes. So principal stresses are so principal stress, first have to find lambda 1. So lambda 1 is the value of this one. So this is the value of lambda 1, this is the value of lambda 2, and lambda 3 is already given in the question because the third row and the third column has 0 of diagonal component. So basically it means the principal plane, the third principal stress basically aligned along the third coordinate axis. So lambda 1 is given by this one, this point. So this is the value of 1 unit and this is the radius of Mohr circle, which is of 8 unit. So 8 minus of minus 1, so radius of 12 unit. So 12 so from here this is the origin and this is complete of 12 units. So what is the distance between this one? So 12 minus of 1, that is 12 minus of 1, that is 11. Lambda 2, so this is the value of 1 unit and this is the value of 12 unit, that is minus of 12 unit. So minus 12 minus 1, that is minus of 13. And what is the value of lambda 3? Already given the question, that is equal to 3 units. Okay, so lambda 3 is 3 unit. So I have interchanged this because always principal stresses are written in the ascending order. That means smaller, bigger to smaller value. So lambda 2, this is basically lambda 2 and this is basically lambda 1. So lambda 2 and this is lambda 1. So we have found the value of the principal stresses. Also in this question we have to find out the principal plane in which these principal stresses are acting. Now coming to the first principal stress, that is lambda 1. So it is acting at this angle from the x plane. We can say this is x plane. So it is acting at this angle. And what is the value of this angle? So we can find out the value of this angle. So this is basically of 12 units and this is 6 root 3. So it is nothing but sine theta is given by 6 root 3 upon 12, that is root 3 by 2. So theta here is 60 degree. So theta here is 60 degree. Okay. And it is mentioned in the so from here we find out that This is a complete 360 rotation, and if we take the minus, that is minus 60 degree from 360 degree, we can know the angle of the first principal plane from the x plane. Okay, so that is lambda 2. So here principal plane. So lambda 1 plane occurs at 360 degree minus 60 degree, that is equal to 300 degree, and it is in which direction? Clockwise. Clockwise from the x plane, or we say even plane. 300 degree clockwise from even plane or x plane. In the Mohr circle. So if it is occur, that is lambda 1 plane occur at 300 degree clockwise from the x plane in Mohr circle. So in the real, in the actual one, it is from the 150 degree counterclockwise, that is anti-clockwise from the x plane in the physical coordinate system. So from this we can say that lambda 1 plane occurs at 150 degree anti-clockwise from the even plane or x plane in physical coordinate system. So here alpha becomes 150 degree, and the plane normal is given by, the plane normal acting on any plane at an angle alpha is given by cos alpha sin alpha 0, which is nothing but cos of 150 degree sin of 150 degree 0. So cos of 150 degree is minus of cos 30 degree, which is nothing but minus root 3 by 2. Sin 30 degree, sin 150 degree is nothing but sin of 30 degree, which is 1 by 2 and 0. So this is a principal plane direction on the lambda 1 plane. Now coming to the lambda 2 plane. So here is the point, that is lambda 2, as you see in the figure, that lambda 2 is here, and this is our x plane. So here if we take the angle, so this angle is nothing but 180. This angle is this complete is 180 degree, and what about this angle? This angle is nothing but 180 minus 60, that is 120 degree. So we can say lambda 2 plane occurs at 180 degree minus 60 degree, that is 120 degree clockwise from the x plane in Mohr circle. So what it means in physical coordinate system? So in physical coordinate system, it means that lambda 2 planes occurs at 60 degree, because it is half of the angle in the Mohr circle. So it is 60 degree counterclockwise from the x plane in the physical coordinate system. So it means lambda 2 plane occurs at 60 degree anti-clockwise from the x plane in physical coordinate system. In physical coordinate system. That is here alpha is 60 degree. So the plane normal is given by, that is a component of plane normal, which is here n2, we say n2 is given by cos alpha sin alpha 0, then cos 60 sin 60 0, cos 60 is 1 by 2, sin 60 is root 3 by 2 and 0. So this is a lambda 2 plane, component of lambda 2 plane. Now the component of lambda 3 plane. So from the stress matrix we see that the lambda 3 plane is acting along the third coordinate axis, which is nothing but E3 coordinate axis. Okay, so lambda 3 plane occurs along E3 plane. So now coming to the first question. The first question says draw a Mohr circle corresponding to this state. We already draw the Mohr circle. The second part is what are the principal stress component and the direction of principal plane. So we find out the principal stress components and as well as the direction of principal planes. And the third question is what is the maximum shear traction and on what plane does it act. So we also have to find out the maximum shear traction. So we have three shear tractions on three different planes, principal planes. So we have to find out the three shear maximum shear traction on the three different principal planes. So the first maximum shear stress on the first principal plane is given by, so that is tau max at first principal plane is lambda 1 minus lambda 2 upon 2. So what is the value of lambda 1 minus 13 minus of 11, lambda 2 is 11 by 2, which is nothing but 12. And we also here we have to find out the plane, that is the principal plane on which the maximum shear stress is acting. So this is the maximum principal plane, that is nothing but 30 degree clockwise from the x plane. This is the value of maximum shear stress on the first plane. So which lies at 30 degree clockwise in the Mohr circle, because this is 60 degree, this angle is 60 degree and this is 30 degree. So it lies at 30 degree clockwise in Mohr circle. So it means 15 degree counterclockwise, that is anti-clockwise, in physical coordinate system. And the component of that plane is given by n1 is equal to plus minus cos of 15 degree sine of 15 degree 0, that is comes out to be 0.9659 0.2588 and 0. So this is the first plane on which the maximum shear stress is acting. Now the second plane on which the maximum shear stress is acting is, so first we have to find out the value of the maximum shear stress on the second plane, that is tau max of 2. So it is nothing but lambda 1 minus lambda 3 upon 2, that is minus 13 minus of 3 by 2, that is equal to 8. So here we know that is the value of lambda 1 and lambda 2 plane. So through this we can find out the maximum shear stress value at this plane, that is lambda 1 and lambda 2 plane. And to find out the maximum shear stress value on the lambda 1 and lambda 3 plane, we have to find out the maximum shear stress corresponding to lambda 1 and lambda 3 plane. So there are two ways to find out the plane on which this maximum shear stress is acting on lambda 1 and lambda 3 plane. So the first way is to using the Mohr circle, or draw the Mohr circle for the lambda 1 and lambda 3 plane. The second way is to find out the, as we know, the lambda 1 and lambda 3 plane are perpendicular to each other. Sorry. So lambda 1 and lambda 3 plane are perpendicular to each other, and the maximum shear plane occurs at 45 degree from the two principal plane. So suppose we have two principal plane, lambda 1, that is lambda 1 and lambda 3. So the maximum shear stress occurs at 45 degree from the two principal plane. So it is nothing, it is basically the resultant. So how we can find out the this plane? We know these two perpendicular plane, and we find out the plane at 45 degree. So basically this is the resultant of these two plane. Okay, so we can found it using this way. And the other way is to draw the Mohr circle corresponding to lambda 1 and lambda 3. So what is the value of lambda 3 here? Lambda 3 is 3. So this lies something here. Lambda 3, sorry, lambda 3 is something lying here. Lambda 3 is 3, and we have to draw another circle with the endpoints lambda 1 and lambda 3. So I am approaching the alternate step, that is find out the resultant of the two principal plane, that is E1 and lambda 1 and lambda 3 plane. So maximum shear stress plane occurs at 45 degree from the lambda 1 lambda 3 planes, or we say the two principal planes, the maximum shear stress occur at 45 degree. And we, the normal lambda 1 plane, that is the normal of lambda 1 plane has been found earlier, that is here. We can find the normal, that is the lambda 1 plane we have found already, so we can directly use here. And lambda 3 plane is nothing but the 0 0 and 1, that is it is along the E3 direction. This plane is along E3 direction. So normal of lambda 1 plane is already found above, and lambda 3 plane is given by 0 0 1, and we have to take the resultant of these two. So the maximum shear plane will have the following normal. That is N2 is equal to 1 by root 2 minus root 3 by 2. So what is the lambda 1 plane normal? So lambda 1 plane normal is minus root 3 by 2, 1 by 2 and 0. So I just write here minus root 3 by 2, 1 by 2 comma 0. And what is the lambda 3 plane? 0 0 1. And we basically take out the resultant because it makes, because the shear plane, maximum shear plane, makes an angle of 45 degree from the two principal plane, that is lambda 1 and lambda 3. So it gives us 1 by root 2 minus root 3 by 2, 1 by 2, 1. So this is a plane corresponding to maximum shear stress. Now the third plane, maximum shear stress corresponding to the third plane. So tau max 3 is given by lambda 2 minus lambda 3 upon 2, which is nothing but, what is lambda 2? 11 minus 3 upon 2, which gives us 4. And the plane on which it is acting is the same, that is we have to find the lambda 2 and lambda 3 plane normal corresponding to lambda 2 and lambda 3. So we already find out the value of lambda 2 plane, okay, and lambda 3 is nothing but 0 0 1. So we have to take the resultant of these two. So the maximum shear plane corresponding to tau max corresponding to tau max 3 is n3 is equal to 1 by root 2. What is the lambda 2 plane normal? So lambda 2 plane we have found above, 1 by 2, root 3 by 2 and 0. 1 by 2, root 3 by 2 and 0. 1 by 2, root 3 by 2, 0 plus 0 0 1. And if we take summation here, then we get 1 by 2, root 3 by 2, 1. So this is about question number 1, that is a part A of problem number 2. So we have found, we have calculated, we have solved the part A problem of question number 2. The second part is, using Mohr circle, find out the normal and shear traction on a plane whose normal lie in xy plane and makes an angle of 15 degree from x-axis in the x direction, in the clockwise direction. So it says that using Mohr circle, we have to find out the normal and shear traction on a plane whose normal lies in xy plane and makes an angle of 15 degree from x-axis in clockwise direction. So in Mohr circle, what it means? So in Mohr circle, it basically the angle becomes double. That means we have to find, that means the xy plane in the Mohr circle, the xy plane makes an angle of 30 degree from the x-axis in counterclockwise direction. So the plane that is we are talking about is that plane. So basically this is our x plane, and from this plane 30 degree from counterclockwise direction. So counterclockwise is this direction, and here it is 30 degree angle. So this is the required plane that we have to find out. The green color denotes the problem number B part. Okay, so part B says 30 degree from the x-axis in counterclockwise direction in Mohr circle. So 30 degree counterclockwise direction from the x-axis. And now what the question is here? So we have to find out the normal and shear component of traction on this plane. So coming to the Mohr circle, what is this point? This is basically angle of 30 degree, and this is the radius that is of 12 units. Sorry, I draw in the wrong figure. So I have to draw in this Mohr circle. (30°). This angle is 30 degree, and we have to find the normal and the shear component of traction on this plane. That is the plane which is denoted by green color. So the radius is of 12 units. So the x component is given by, that is the sigma. So this is problem number 2b solution. So I just draw one more circle here to better understand. This is -1, 0, and this is somewhere -7, 6√3, and this is your radius. And through this we draw more circle. And the question, it is mentioned that 30 degree counterclockwise from the x-axis. So this is 30 degree, this also becomes 30 degree, and we have to find here what is the sigma and tau. So sigma is given by, so this is nothing but -13, 0, this is 11, 0, this is the sigma value, and this is the shear stress value, tau. So sigma is -1, because this is -1 plus r cos 30. See, this is r and this is 30, so this is r cos 30. -1 minus r cos 30, which is nothing but -1 minus 12 into √3/2. So it will coming out to be 11.39. Next one is shear stress tau. So tau is r sin 30. It's a simple way, r sin 30, because this is r sin 30. So tau is equal to r sin 30. What is r is 12 into 1/2, that is 6 unit. So this is the part B of the second question. Now coming to the part C, 2C. So third question is, using more find out the octahedral normal and the shear stress component corresponding to these states of stress. So octahedral normal and the shear stress component. So first we have to find octahedral normal stress. So in the starting of this lecture, I have written the formula of octahedral normal stress, which is nothing but 1/3 of first invariant of the stress matrix. So 1/3 of sigma 11 plus sigma 22 plus sigma 33 upon 3, which is nothing but -7 plus 5 plus 3. So after calculating this one, we will get 1/3. So this is the octahedral normal stress. Now coming to the octahedral shear stress. Octahedral shear stress is given by 1/3 2 times first invariant square minus 6 times second invariant. So first we have to find out the second invariant, which is given by sigma 11 sigma 22 plus sigma 22 sigma 33 plus sigma 33 sigma 11 minus tau 12 square minus tau 23 square minus tau 31 square. Okay, so when we calculate this and after putting the values of sigma 11 sigma 22 sigma 33 tau 12 tau 23 and tau 31, we will get the second invariant is equal to minus of 149. Tau octahedral, that is the shear stress, octahedral shear stress component is given by 1 by 3 root over 2 times 1 by 3 का whole square 1 by 3 whole square minus 6 times I2, which is coming out to be minus of 149. So after calculating this, we will get 9.977 approximately. So this is the octahedral shear stress for this problem. Shear component of octahedral shear stress, and this is the octahedral normal stress component, which is equal to 1 by 3. So this is the question number C of second problem. So the third part of the question was find out the octahedral normal and the shear stress component corresponding to this state of stress. We already find out. The last part of this question is decompose the given stress matrix into hydrostatic and deviatoric part. Let's come to the last part of this question, that is we have to decompose the given stress matrix into deviatoric and hydrostatic part. So first we have to find the hydrostatic part. Hydrostatic part of given stress matrix is nothing but 1 by 3 times identity tensor. That is 1 by 3, 1 by 3, 1 by 3, and all the off diagonal components are 0. The next part is deviatoric part. Deviatoric part of given stress matrix. So the deviatoric part of stress matrix, that is sigma d, is given by total stress matrix, component of total stress matrix minus hydrostatic part. So that is minus 7. First we will write the total stress matrix, that is equal to minus 7 6 root 3 6 root 3 5 and 003 minus 7 minus 7 6 root 3 0 6 root 3 5 0 0 0 3, and we have to subtract the value of hydrostatic part, that is minus 1 by 3 minus 1 by 3 minus 1 by 3. So we will get minus 22 by 3, 6 root 3, 0, 6 root 3, 14 by 3, 0, 0, 0, 8 by 3. So this is the value of deviatoric part and this is the value of hydrostatic part. So the fourth last part of this question was decompose the given stress matrix into hydrostatic and deviatoric part, which I already solved the questions. So all the parts of this question has been solved. So anyone have any doubt, please ask and unmute yourself. Okay, so let's move on to the next question. That is problem number 3. So this is a multiple choice question problem. So the question is, consider a horizontal bar which is stretched by the application of an axial force. The initial length of the bar is 1 meter, while the final length of the bar is 1.1 meter. So the question is, which of the following statements are true? Which of the following statements are true? Okay, so the option is the stretch in the bar is 0.1. The second option is the stretch in the bar is 1.1. The third option is the stretch cannot be found unless the magnitude of force is provided. Unless the magnitude of force is provided. And the last option is none of the above. So now coming to the question, the question says, consider a horizontal bar which is stretched by the application of an axial force. The initial length of the bar is 1 meter, while the final length of the bar is 1.1 meter. Which of the following statements are true? The stretch in the bar is 0.1 unit, 0.1. The stretch in the bar is 1.1. The stretch cannot be found unless the magnitude of force is provided. And the last option is none of the above. So as we know that stretch is given by final length upon initial length. So after deformation, what is the final length of the bar? So it is given in the question that final length of the bar becomes 1.1 meter. And what is the initial length of the bar? Which is 1 meter. So the stretch is coming out to be 1.1. So the correct option is option number B. Now coming to the next question, that is problem number 4. This is also a multiple choice question. The deformation gradient tensor can be expressed in terms of the displacements. In terms of the displacements. As the option is I, that means identity tensor, minus grade of u. The second option is grade of u, that means gradient of u. The third option is I plus gradient of u. And the last option is minus of gradient of u. Here, gradient of u is nothing but the displacement. U is displacement vector. Now come to the question. So this question says the deformation gradient tensor can be expressed in terms of the displacement as. So the deformation gradient tensor is denoted by big F, and it can be expressed in terms of displacement as the option is I minus grade u. Is it correct? No, this is not correct. The second option is grade u, that means the gradient of displacement vector. No, that's also not correct. The third option is identity plus gradient of u, that means the identity plus the gradient of displacement vector. So yes, this is the correct option. In the starting of the session, I already mentioned the formula for the deformation gradient tensor in terms of the displacement vector. So it is given by identity plus gradient of u, that is the gradient of displacement vector. The fourth option is minus of gradient of u. No, this is also not correct. So this is the question number 4. So the question number 3, in the question number 3, I would like to mention one thing, that if the same problem is there, but the problem is such a way that we are not asking about the stretch value, we are asking about the strain value. So what is the value of the strain in this case? So if we found the value of a strain in this case, so strain is nothing but change in length upon initial length. And what is the change in length? So change in length is basically final length minus initial length upon initial length. So what is the final length? 1.1. What is the initial length? 1. And what is the initial length? 1. So it basically comes out to be 0.1. So the first option will be correct if we ask about the strain value. What is the strain in this case? But here the question is asking about the stretch value. Therefore, the first option will be incorrect. But please don't confuse with that question, because stretch and strain are two different parameters through which we can measure the value of the deformation in the line element. Okay. So if we find out the strain value, we have to basically take the difference in the length value, that is the difference in final length after deformation and the initial length before deformation. So the change in length in this case is given by 1.1 minus 1, and the initial length is as the denominator, as in the denominator as same as in the stretch definition. So 1.1 minus 1 upon 1, that is equal to 0.1. So the strain value in this case is 0.1, but the stretch value in this case is 1.1. Now coming to the next question. So this is the last question of this session, that is problem number 5. So this question is also a multiple choice question. Which of the following option is correct? Which of the following option is are correct. That means there may be a more than one correct option in this case. Maybe only one is correct, or maybe all of the options are correct, or maybe only two or three are correct. So what is the option here? The first option is gradient of a scalar. Gradient of a scalar is a second order tensor. The second option is gradient of a vector. Gradient of a vector is a second order tensor. Gradient of a vector is a second order tensor. And the third option is gradient of scalar. Gradient of a scalar is a first order tensor. Gradient of a scalar is a first order tensor. And the last option is gradient of a scalar. Sorry, gradient of a scalar. Gradient of a scalar is a vector. So the question is which of the following options are correct? Gradient of a scalar is a second order tensor. Gradient of a vector is a second order tensor. Gradient of a scalar is a first order tensor, and the gradient of a scalar is a vector. So first thing I would like to mention here that if we take a gradient of any, whether it is a vector, tensor or higher order tensor, basically it increases the order of a tensor. So gradient of a tensor, gradient of any scalar, vector or tensors, gradient of any quantity increases the order of the tensor by 1 So basically if we take gradient of any physical quantity, so it increases the order of the particular quantity by 1. Suppose if it is a fourth order tensor, so it becomes fifth order tensor, or it's a second order tensor, then it becomes third order tensor, or if it's a first order tensor, then it becomes a second order tensor. So gradient of any quantity increases the order of a tensor by 1. So the now come to the question. So the first question is gradient of a scalar is a second order tensor. So is this correct? Scalar is a first order tensor. That means if it is correct, then it means that scalar is a first order tensor, and if we take its gradient, then it becomes a second order tensor. So no, this is not correct because scalar is a zeroth order tensor. Scalar is a zero order tensor. And if we take the gradient, it becomes a first order tensor, not a second order tensor. So it is incorrect option. Now the next question, gradient of a vector is a second order tensor. Is it correct or not? So vector is a first order tensor. Vector is a first order tensor. And if we take the gradient of this vector, it becomes a second order tensor, which is correct. Then third option is gradient of a scalar is a first order tensor. So a scalar, as I told earlier, that it is a zero order tensor. As I also mentioned in this case, that scalar is a zero order tensor, and if we take the gradient, the order increases by 1 and it becomes a first order tensor. So yeah, this option is also correct. The last option is gradient of a scalar is a vector. So what is a scalar quantity? Scalar is basically a zero order tensor. And what is a vector quantity? It is basically a first order tensor. And if we take the gradient, that means if we take the gradient of a zero order tensor, so it becomes the first order tensor. And what is the first order tensor? So first order tensor is basically a vector. So yeah, this is also a correct option. So this is question number 5. Here, one thing more I want to mention here, that it is about gradient. Suppose this question is asked in another way, that if we take the divergence, so if divergence of a scalar or divergence of a vector or divergence of a first order tensor or any higher order tensor, so basically divergence reduces the order of a tensor. So just opposite to the gradient, because gradient increases the order of a tensor by 1, but divergence reduces the order of a tensor. So I also write here, divergence of any quantity decreases the order of tensor. Okay, so this is all about session number 4, in which I have covered 2 lectures, lecture number 9, lecture number 10 and lecture number 11, which is based on the Mohr circle and the concept of some basic strain. So in this session I have solved 5 problems, in which the first 2 problems were based on the Mohr circle, which is one of the most important concept to find out the principal stress and principal plane. The next 3 questions I solved is based on the stretch, the deformation gradient tensor, and the normally tensor concept. Okay, the last 3 questions basically point out the concepts that you already covered under lecture 1 to lecture number 10. And the more detailed part for this strain concept will be coming in the next session, in which lecture 12, 13 and 14 will be covered. So yeah, this is all about today's session. I hope you have enjoyed the session, and if anyone have any doubt, you can also write in the chat box, or you can also comment in the YouTube, where this recording will be posted there. So you can get this link, you can get the recorded session of this session in the NPTEL website, where the course is mentioned, or solid mechanics course is mentioned. You can get the link from there, and from there you can watch the recording of the session. So yeah, that's all for this session today. Thank you for the joining. See you in the next session, which will be conducting in the coming Friday. So thank you. You may leave the meeting.